This is problem 3 on exam 2 in module 2, which is on page 50 in the book Problem Solving Guide for Electromagnetism and Optics. Problem 3 is a solid non-conducting sphere has a net charge of 1.2 nanocoulombs uniformly distributed throughout its volume in a radius of 2 centimeters. It is surrounded by a conducting shell of radius 4 centimeters and thickness 1 millimeter that has a net charge of minus 0.8 nanocoulombs. So minus 0.8 on the shell, plus 1.2 on the non-conducting sphere. A, what is the electric field at a distance 3 centimeters from the center of the non-conducting sphere? B, what is the electric field at a distance of 6 centimeters from the center of the non-conducting sphere? Part C, what is the electric field at a distance of 1 centimeter from the center of the non-conducting sphere? And part D, what is the net charge on the outer surface of the spherical shell? We need a good diagram. Let's look at a cross section. We have to remember that's not a circle. Those are spheres. Cross section of a sphere. The non-conducting sphere has a net charge of 1.2. Let's put it in there, 1.2 nanocoulombs. The conducting spherical shell, minus 0.8 nanocoulombs. There's the charge on the shell. I think we're ready to go. Part A says, what's the field at a distance of 3 centimeters, which is right between the solid non-conducting sphere and the shell. If we need the field there, let's put a Gaussian surface there, and remember these are spheres, not cylinders. So there is a sphere of radius 3 centimeters. Gauss's law, E dot A is 4 pi kq enclosed. There's only one surface on a sphere. The surface area is 4 pi r squared. The field lines are hitting the sphere at right angles everywhere. So E dot A is just E times A. Q enclosed is plus 1.2 nanocoulombs, and we're ready to go. There's the area of the sphere, 4 pi r squared, convert it to SI units, and 4 pi k Q enclosed, converting that to coulombs. We can solve for E, and we get 12,000 newtons every coulomb, and since the charge is positive on the non-conducting sphere, we know it's radially outward. So part A, the electric field 3 centimeters away from the center of the solid sphere is 12,000 newtons per coulomb radially outward. Part B, what's the electric field 6 centimeters away from the center of the non-conducting sphere? That's outside the spherical shell. Let's put the Gaussian surface there. It's a sphere, not a cylinder. That's a sphere. Cross section of a sphere. Gauss's law, E dot A is 4 pi kq enclosed. The charge enclosed, we have plus 1.2 here, minus 0.8 here. That's a net of plus 0.4. All of that is inside of our Gaussian surface. The radius of the Gaussian surface, 6 centimeters, 0.06 meters. We can solve for E, and we get 1,000. And its positive charge, it's a net positive charge, so it's also radially outward. The electric field 6 centimeters away from the center of the solid non-conducting sphere is 1,000 newtons per coulomb radially outward. Now we can do part C. Part C asks for the field 1 centimeter from the center of the non-conducting sphere, and that is inside the non-conducting sphere. So there it is. If this was a conducting sphere, all of the charge would be on the outside and none would be inside our Gaussian surface. But it's non-conducting. The charges want to move, but they can't. So we have to figure out how much charge is inside this sphere, our Gaussian sphere of radius 1 centimeter. Don't say it's half. It's not even 1/4. We know that the charge is uniformly distributed throughout the volume. One way to tackle this problem is to say how much volume does the whole sphere have, and how much volume does this have? Since it's uniformly distributed, it's going to be that ratio. The volume of a sphere of 2 centimeter radius, the equation is 4/3 pi r cubed. We stick 2 centimeters in from the radius, and we get 8 cubic centimeters times 4/3 pi. For a 1 centimeter radius cube, 1 cubed is 1, so we get 4/3 pi times 1 cubic centimeter. So the volume of a sphere of radius 2 centimeters is 8 times the volume of a sphere of 1 centimeter. If the radius is doubled, the volume is octupled, 8 times bigger. So the charge on the inner sphere is 1/8. Only 1/8 of the charge on the sphere is within 1 centimeter of the center. So we divide the total charge by 8 to get Q enclosed inside of our Gaussian surface. Now we can apply Gauss's law because we know Q enclosed. E dot A is 4 pi k Q enclosed. The area is still a sphere, but it's a radius of only 1 centimeter, and Q enclosed is only 0.15 nanocoulombs. Converting that to coulombs, we get 13,500 newtons every coulomb, and it is positive, so this is also directly away. So the answer to part C, the electric field 1 centimeter away from the center of the solid conducting sphere, is 13,500 newtons per coulomb radially outward. Finally, we can get to part D. What is the net charge on the outer surface of the spherical shell? We know the net charge on the spherical shell is 0.8 nanocoulombs negative, that's given. But the field lines emanating from this non-conducting sphere all have to end. There can't be any field inside of the conducting shell. So there must be minus 1.2 nanocoulombs on the inner surface of the conducting spherical shell. These electrons will get pulled in. There's positive 1.2 nanocoulombs here. The electrons on this conducting spherical shell, 1.2 coulombs of them, will get pulled to the inner surface. So there has to be minus 1.2 nanocoulombs of charge on the inner surface. If we know there's minus 1.2 nanocoulombs on the inner surface and the total is minus 0.8, seems like there's got to be plus 0.4 nanocoulombs on the outer surface. So the answer is the charge on the outer surface of the conducting sphere is plus 0.4 nanocoulombs. And that's problem 3.